Hello, and welcome back to another Math 104 lecture. So, just catching up with what we did last time, where we left off was we talked about the properties of logarithms, and there were 4 properties of logarithms detailed before. I walked you through a couple proofs of them, and then your last classwork assignment was evaluating some, logarithmic forms and getting, an actual value from them using the properties that we had discussed earlier. So what I want to do today is, especially because I didn't have time to do an example of it before, I want to do an example of finding the domain of a logarithm, so that way we all have a good idea of how to do it. Now, I know that there was a logarithm domain on the previous homework, and that's okay. The reason that it was okay was because I know that I had mentioned the domain of a logarithm had to be from 0 to infinity, right? So that should have been an indication for you that whatever value was inside your logarithm, you were supposed to set to be greater than 0, because 0 can't be included, hence the parentheses, and also the negative numbers could also not be included. So what we're going to start with today is we're going to start with another example of domain of a logarithm. So let's say we have a function, and our function f is defined by log of 4 minus x squared. Okay, now again, what I just said was that the domain of a logarithm has to be positive numbers. Everything that's inside here, inside the logarithm, you can only get positive numbers for. If you get anything other than a positive number in here, if you get 0 or a negative number, that logarithm is not defined. It will not work out. So what we have to do to figure out the domain is we have to take the piece that's inside the logarithm and set it to be greater than 0. Okay, notice it's not greater than or equal to, because again, 0 is not allowed. So we say, okay, sure, 4 minus x squared is greater than 0. To figure this out, we need to factor. So factoring this, we have 2 minus x and also 2 plus x. How did I factor that? Difference of squares, right? Normally we're used to seeing it as something like x squared minus 4, and you can jump and say that this is difference of squares, but this is still also difference of squares. It's just in the order that we're not used to seeing it, right? 4 is the same thing as 2 squared. So this is the same thing as 2 squared. So we have a square here, and difference. So yeah, sure, difference of squares. And the way that you factor difference of squares is a plus b times a minus b. Order doesn't matter, so you could write the minus first, and that's totally okay. So we get 2 minus x times 2 plus x is greater than 0. Now at this point, going back to inequalities, hopefully you realize at this point, before you even factored, that you have a quadratic inside of an inequality. And the only way that we can solve these is with test points. When we have something higher than a linear, we have to use test points to be able to figure out what intervals work and what intervals don't work. But to be able to test intervals, you obviously need to plot points onto the graph to figure out what your intervals are, right? So to figure that out, well, we set each factor to be equal to 0, because we need to find when the inequality actually is 0. So we have 2 minus x is equal to 0 and 2 plus x is equal to 0. So for the one on the left, we get, if you add x to both sides, you get 2 is equal to x, or x is equal to 2. And then on the one on the right, if you subtract 2, you get x is equal to negative 2. So x is equal to plus or minus 2. So these are the 2 points that we're going to be plugging in onto our number line here. So we have negative 2 and 2. And this, again, before we even get to intervals, we have to ask ourselves, what kind of circles do we put on negative 2 and 2? Well, because it is greater than 0, not greater than or equal to, we found the 2 points that make the inequality 0, but we don't want 0. So we have open points on them, open circles. So now we have 3 points that we have to test. 1, 2, and 3. And for these, we have to pick test points. I, of course, I love to pick the easy points. So negative 3, 0, and 3. Feel free to pick any point that is in those intervals, that as long as you're not picking the actual points that make it 0, such as negative 2 and 2, you should be fine. So let's go ahead and test these. So what our test normally is, well, we're plugging in our number to see whether or not we get a negative or a positive number, right? And in this case, because we're looking for it to be greater than 0, we're looking for only positive intervals. If we get anything other than a positive interval, if we get a negative interval, then we don't want that, right? We exclude that from our domain. So we're testing -3 first. And when we test -3, that means we're going to have, and just to rewrite this, again, our factored version is 2 minus x and 2 plus x. So that's what we're plugging into here. And so when we plug in -3, we have 2 minus a -3 and 2 plus a -3, which is the same thing as 2 minus 3. So 2 minus a -3, we can simplify this down. This is 2 plus 3. So when we simplify this, we get, well, this becomes positive. 2 plus 3 is positive. 2 minus 3 is negative. So positive times a negative gives you a negative. Is a negative greater than 0? No, right? So we exclude that. We don't want that interval. So this interval over here, this is negative. So we don't want that. So now we test the middle interval. So 0. So we have 2 minus 0 and 2 plus 0, right? And for that, well, 2 minus 0 is positive. 2 plus 0 is also positive. So we get positive times a positive, which is positive. And is a positive greater than 0? Yeah, it is. Hooray. So we have one interval so far that works. So our middle interval is, in fact, going to be part of our domain. And now we just have to test 3. So to test 3, well, again, we have 2 minus 3, or I'm sorry, well, the first one was addition, right? No, it wasn't. It was subtraction. I lied. 2 minus 3, and then we have 2 plus 3. And now what do we get? Well, we actually end up getting the same result that we had the first time when we plugged -3 in, and we get a negative times a positive. The only thing that happened differently was that we got the positive and negative in reverse order, but still positive times a negative or negative times a positive. Either way, it gives you a negative. Is a negative greater than 0? Nope, it is not. So we know that this interval is also excluded. So the only interval that works, the only interval that's going to be part of our domain here is going to be this middle interval in, right in the middle, the piece that goes from -2 to 2. And the way that we write that, and the way that you would write your domain is, again, the domain of f, your function f, is -2 to 2, parentheses, because we are not including those numbers. So that's it. Again, nothing outlandish, nothing that we haven't seen before. This is all, stuff that we should be familiar with. Test points, finding a domain. The only caveat is you had to figure out this piece right here, how to start things off. And the way that you start things off for a logarithm is you always set the piece that's inside the logarithm to be greater than 0. That's always how you try to figure out the domain of a log. And if there's multiple logs, as there were with the last homework, well, then you just figure out the domain of each logarithm. And then if it's all part of one function, then, you're just going to omit the parts where they disagree. But in this case, we only had just the one log, so that's it. Just our domain is -2 to 2. Okay, so there was one thing that I may have mentioned in the last lecture, but I don't remember if I did, so I just want to make sure that I clarify. If you have log of any number, I'll just put x right here, right? And you don't have a base, as in the base is hidden, we call this the common log. And the common log is equivalent to log of base 10 of that same value. So the idea here is just that if you have a base of 10, we call this the common log, and you can just omit writing the 10. And you would just, have this blank space here. It is assumed if your logarithm has a blank space for a base, that the base is 10. So again, this is just to write it out. This is known as the common log. And the reason that I'm going over this one more time is because there is actually one more type of logarithm that we're going to get to in just a second here, and that is called the natural log. But before we move on, just want to, again, hammer this down. If the space is omitted, again, it is assumed to just be a 10, in the same way that if you had square root of x, Notice that the index is missing, right? It is assumed that the index is a 2 to clarify that this is a square root. And also in the same way that if you have any number and it's not raised to any power, the hidden power here is a 1. Okay, so in mathematics, it's definitely not uncommon for things to just be assumed to be something if we omit that information. And this is just one of those things. Again, common logarithm, the space here would just indicate that your base is a 10. Okay, all right, so natural log. Natural log. What is a natural log? Well, if a common log is where we have, a specific base in mind, and for a common log, the base is 10, a natural log is going to be very similar, with the exception that your base is going to be e. Remember, e is Euler's number, right? We discussed this before. E is that, 2.71819, so on and so forth. It's irrational, goes on forever. So if you have something in this form with a log of base e on your value x, then this is known as the natural log, which you write as ln x. Okay, so you would write this. So this, if you wrote it on the side that's, on the left, this is not necessarily incorrect, but it's also not common practice. You should definitely get used to writing things, if your base is in terms of e, you should absolutely get used to writing things as just ln, whatever your value is. So just to emphasize, if you had log base e of, let's just say, I don't know, x squared plus 4, for example, whatever your value is that's tied to that first logarithm, this is the same thing as natural log of x squared plus 4. Okay, so the entire idea is we just use these terminologies to specify specific bases. Common log, your specific base in that case is a 10. Natural log, your specific base is an e, and you write ln for natural log. Okay, that's how you assume that, the hiding base is going to be an e. Okay, so there's actually some properties that go along with natural logs, but these properties tie very much into the same properties that we discussed in the last lecture. So we have 4 properties, once again, 1, 2, 3, 4, and the 4 properties are, if you have the natural log of e, your value is 1. Why is this the case? Well, remember, the first property I gave you guys is if you have log with some base a, and this is on the same matching value, right? It's base a with the value of a, your answer is 1. And when we converted this to exponential form, again, you can convert back and forth. We know that this is the same thing as a to the first power is equal to a, and yeah, a to the first power is absolutely equal to a. So this is the first rule here is just a direct translation of our first property from regular logarithms. Same thing with our second property. If we have natural log of 1, this is equal to 0. Why is this the case? Once again, this is the same thing as if we had log base e value 1, and if, this is equal to 0, well, translate this to exponential form. Exponential form, this is e to the 0 is equal to 1. And remember, any number to the 0 power is always going to be 1, even if it's an irrational number. 2.71819, yada, 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 to the 0 power is still equal to 1. So this still directly falls out of our logarithm properties. Thirdly, if you have the natural log of e to the x, where, again, x is some exponent, this is always going to equal whatever that exponent is. So the idea here is if you have the natural log and you have an e put together like this, so e is going to be, your value of the natural log, these will always cancel out. So what happens if your exponent is just 1? So what happens if you have, for example, and I'll write this in blue just as a hypothetical, if you have ln e, well, ln e to the first power, notice how that's just this piece, ln e to the first power. And so we see here that, oh yeah, x is, your exponent, and 1, that's your exponent. So we can see here that 1 and 3 kind of tie together here, but the entire idea is just that your ln, your natural log, and your e are going to be canceling out here. The natural log and e should be canceling out in some shape, way, or form. Okay, and then last but not least, if x is greater than 0, I'll put this in parentheses, then you have this rule, e to the ln x is also equal to x. Remember from at the end of the last lecture how I proved 3 and 4, and 3 and 4 were essentially just consequences of having an inverse function composed with the regular function. And whenever you compose a regular function with its inverse, you should always get just your initial input back, so your initial variable. This is the same idea. If you have ln, so for rule 3, if you have ln e to the x, you should just get x back. And for rule 4, if you have e to the ln x, then you should still just get x back. I'm not going to worry about proving these because the proofs are exactly the same as proving the proofs that I did in the last lecture, but the idea is still, there, that you should still just be getting x back regardless if you have e to the x inside your logarithm or if your logarithm is the exponent of your Euler's number e. Okay, and the reason that, again, we have this piece if x is greater than 0 is because the same idea that we had before, which is whenever you compose functions, you always have to worry about the domain of the inner function first before you can worry about the domain of the composition. And so we're worried about the domain of ln x. And we just talked about how the domain of logarithms has to be a positive number, right? So as long as x is positive, then rule 4 works. If x is negative, then this in fact will not work. Well, if x is negative, then that actually falls apart because you can't have a natural log of a negative number. Okay, so those are your 4 natural log properties, but again, notice how they're basically identical to the 4 properties of regular logarithms. So as long as you can remember one or the other, whether it's the natural log properties or the regular properties, you should be totally okay. I strongly recommend remembering these ones because natural log kind of tends to come up a little bit more often than regular logarithms, especially in higher mathematics. But as long as you can remember one or the other, they do directly translate, so you should be fine. Okay, so let's do some work with these in particular. Let's say, and this is, I believe, your first classwork assignment. What I want you guys to do is I want you to evaluate the following. There's 2 things I want you to evaluate. So I want you to go through and evaluate the natural log of 1 over e squared. And then what I also want you to evaluate is e to the ln 4. So e to the natural log of 4. So figure out both of these, see what you come up with, and we will go through these in just a second. Okay, so let's do the first one. Let's do natural log of 1 over e squared. So how do we tackle this? Natural log of 1 over e squared. Well, we don't have a rule for handling the natural log of a fraction with e. Our only rule right now is natural log of e to some exponent, right? So 1 and 3 are essentially identical. 1 is just a special case of 3 because with 1, your power is just 1, right? It's e to the first power, and you would just get 1 back, right? So with 3, that's the one that I'm going to be trying to use here. So I want to try to get this to be in the form of natural log of e to some power. If I can do that, then whatever my power is my answer. That's it. So I have 1 over e squared. Let's use our exponent rules to try to mess with this piece right here. So this is going to be the same thing as the natural log of, well, whenever I have a fraction, and it's in the form of 1 over whatever the case, I know by my exponent rules I can always flip that back to be an integer raised to a negative exponent, right? If I have, for example, 1 over 7, this is the same thing as 7 to the negative first power. If I told you to evaluate 12 to the negative first power, this is the same thing as 1 over 12, right? So we know our exponent rules allow us to go back and forth between integers and fractions. So what I'm going to do is I'm going to take, well, I should say numbers and fractions because e is not an integer. So what I'm going to do is I'm going to take, I have e to the second power, right? But it's in the denominator of my fraction. So to raise it to be, in the numerator, I have to flip the fraction on its head. And to do that, I have to negate the exponent. So this is e to the negative 2 power. And now what my third property allows me to do is that if I have the natural log of e to any power, that power is going to be the result of the answer, or the answer here. That's going to be my result. So our final answer is just negative 2. The natural log of e raised to the negative 2 power is just negative 2. Also, I want to notate really quickly the where the exponent is going. So there's a lot of parentheses that get omitted when you're dealing with natural logs. The way that you can think about it is that there is the outer parentheses of that go to the natural log, and then there's also the inner parentheses that deal with, where the exponent is actually going, right? So we have that negative 2 being applied to e, but notice that the negative 2 is within the natural log. If it wasn't, we have a problem. If we had, hypothetically, I'm going to write this in red, if we had the natural log of e and then the whole thing was being raised to the negative 2 power, your answer would not be negative 2. Because why? What is ln e? Well, ln e is just 1, right? The natural log of e is always going to cancel out to just give you 1. So this is the same thing as 1 to the negative 2 power, and this is just 1. So be very, very careful on understanding where the exponent is actually being applied. If your exponent is being applied to the entire logarithm, that is going to drastically change your answer, as opposed to what we have here, which, originally we had the parentheses omitted, but it's understood in general that if you have an exponent and the parentheses are omitted, the exponent is just being applied to whatever's inside your logarithm, okay? So up here, again, notice the exponent is outside of the logarithm. Okay, I just wanted to touch on that before we did the second evaluation. So the second one that we have to do is e to the ln of 4. Well, we have a rule for this, right? What our rule says is that if we have e raised to the natural log, as long as the number inside the natural log is positive, which it is, it's positive 4, well, then e and the natural log should just cancel out, and all we should be left with is whatever is inside that natural log. So we should simply just get 4 back. And this is directly as a result of our fourth property, which is right here. Again, if we have e raised to the natural log of any number, whatever that number is your answer. Okay, so that's it. That's how we use our properties. That's how we do some evaluations. And that's also how you simplify harder and harder problems. Okay, all right, let's go ahead and clear this off and move on to the next topic. So when we were talking about exponential functions, we came across the idea of interest, right? And what we talked about was continuous compound interest. Continuous compound interest is where we had the following formula. We had A is equal to P times E to the RT, right? And just as a quick refresher, what did all of these variables mean? A was your total, P was your principal or initial amount, E was, well, E is E. That's not a variable. That is a number. And then that's being raised to the RT, where R is your interest rate and T is the amount of time in terms of years, right? So this is something that we were given. And what I want you to take away from this is notice that this is, in fact, an exponential function, right? A is your dependent variable. This is, you could, in fact, even write this as a function. This is essentially A of t, right? Where this is a function of time. Depending how long you're doing your interest, well, then that drastically changes your total. So what we want to do here is maybe we want to think about interest, not necessarily in terms of what our total result would be, but maybe we actually have that knowledge. Let's say, for example, we knew what the principal amount was and we knew the amount that we would get in the end, but let's say we didn't know the rate or we didn't know the time. How could we possibly solve for R or T in this case? Essentially what I'm asking you is, how could we possibly solve for an exponent? Well, remember what a logarithm is supposed to do. If we have something in exponential form, a logarithm is supposed to take your exponential form and translate it so that way the exponent that was originally in your exponential form now becomes the answer to the logarithm. So what I want to do is I want to first isolate the e. So I'm going to divide both sides by p here. So I have a over p is equal to e to the RT. Okay, so the next thing that I'm going to do is I have to think about, okay, well, I want to cancel out this e. If I can get rid of the e, then I would just have the rate and the time on the right-hand side, and that's perfect because, maybe sometimes that's what I'm looking for. Maybe I do genuinely just want to find out what my interest rate has to be, or, how long something has to accumulate for me to get, a certain amount of money, right? So we think about this, and what we just discussed earlier was we had those properties where, if you remember, the natural log of e to the x just gave you x, right? This was the third property that we just had, that we just talked about. So what this tells you is that if I can take the natural log of e to the anything, that anything is what I have left. So what I'm going to do here is I'm going to take the natural log of both sides. Now, this might seem like an odd concept, taking the natural log. Essentially, natural log is a function. So, but whatever you do to one side, as long as you do it to the other side of an equation, it's still balanced. It's still equal. So I'm going to take the natural log of e to the RT on the right-hand side, and whatever I do to the right, I'm also going to do to the left. So I have the natural log of a over p. And last but not least here, I'm just going to bring down this natural log on the left side, natural log of a over p. And on the right-hand side, what should happen? Well, remember, natural log and the e should cancel out, and whatever's left in the exponent should just be just that. It should just be whatever's left. So these pieces are going to cancel out, and we're just left with r times t. So what we just did is we converted something in exponential form. We converted our compound interest formula in exponential form to still be a compound interest formula, but now it's just in logarithmic form. And what this allows us to do is it now allows us to freely solve for r or freely solve for t. So we're going to do an example here in just a second, but the main takeaway here is notice the back and forth that we can do to go from, logarithmic form to exponential form, or vice versa. Okay, so let's do this example. What I want to do is I want to figure out, let's say, I ran out of room over there. Okay, let's say I want to figure out how long it takes to triple your money if it earns 6.5% interest compounded continuously. Give me 1 second and I'll write that out and I will repeat myself. So how long it take to triple your money if it earns 6.5% interest. I misspelled interest again. I think that was the second time I did that. If it earns 6.5% interest compounded continuously. Okay, so what's my idea here? The idea is obviously compounded continuously lets you know you're going to need the continuous compound interest formula. Now, you might not necessarily know which version of it you need. You might not necessarily know if you need it in exponential form or if you need it in the logarithmic form, right? Again, both of these forms are identical. They mean the exact same thing. It's just that one allows you to freely solve for one variable, while one form allows you to freely solve for a different variable. So here in exponential form, this allows you to freely solve for your total, or it allows you to solve for your principal amount, right? If I gave you the rate and the time that this took, and then I gave you either the total or the principal amount, you could find the other one. However, based off the exponential form, there's no way you could find, the rate or the interest. You would have to convert it to the logarithmic form. So the logarithmic form, notice how it's substantially more difficult to solve for a or p because it's inside of a natural log, but it's way easier to solve for either r or t now because it's not attached, it's not the exponent of, your number e. So again, we ask ourselves, well, what are we actually looking for? It says, how long will it take? What we're looking for here is t. We're looking for the amount of time that it takes in terms of years for this to occur, for you to triple your money. So we know t is our unknown. That's what we're looking for here. Okay, let's write out what else we know. We also know our interest rate, right? 6.5% interest. So R is 6.5%. And when I write that from percents, that's the same thing as 0.065. Okay, great. So we know T, we know R. Okay, well, do we know P or A? Do we have a certain amount of money that we're putting in? And do we have a certain amount of money that we know we're going to get at the end? Well, we know for fact what we're supposed to get in the end is 3 times the amount that we started with, right? So we know that A is going to be 3 times whatever your initial amount was, right? And so we can say A is essentially 3 times P. A is 3 times whatever your initial investment was, because again, the question is asking how long it takes to triple your investment. And before we continue, again, our takeaway here is we have to use the logarithmic form because we're solving for T. So writing this in logarithmic form, this is the natural log of A over P is equal to RT. Let's start filling in some things and see if we can make some sense of this. Well, we know what A is, right? We just discussed A, your total, is 3 times your initial investment, right? So 3 over P. Do we know what our initial investment is? Well, no, so we'll just write P is equal to our rate, which is 0.065 times T, and T is what we're solving for here, right? That is our unknown. Okay, so the good news here is it actually doesn't matter what your initial investment is, because we're just looking to see how long it takes to triple that investment. So if your investment, say hypothetically, I'll just write it over here, if your investment was $100, then your A would be 3 times 100. It would be 300, right? If your investment was, $500, then A would be 1,500. So in general, it's not going to matter because A is always identified as 3 times your initial. So as a result, because we're dividing by our initial investment anyway in this formula, our initial investments just cancel out, right? 3P divided by 3P divided by P, well, P over P just cancels. It doesn't matter what your initial investment is because we're just looking to see how long it takes to triple it. So great, that works out. So now what we have on the left-hand side is the natural log of 3 is equal to 0.065t. And now at this point, you're just solving for t. And to solve for any variable in any case, that means isolate it, right? So to isolate, we're just going to divide both sides by 0.065. So divide both sides by 0.065. I don't know why I did that. We get natural log of 3 over 0.065 is equal to t. And at this point, if you were on a quiz and you didn't have or if this were on a test or a quiz and you didn't have a calculator, this is a totally acceptable answer. There's really nothing else that you can do. I don't expect you to know the natural log of 3 off the top of your head, and I certainly don't expect you to know how to divide it by 0.065. But if you were to plug it into a calculator, your final result would be t is approximately 16.9, which says that it takes almost 17 years for you to triple your investment at this interest rate of 0.65 if you're compounding continuously, regardless of what your initial investment is. If your initial investment is $1 or your initial investment is $1 million, that doesn't matter. Notice how your initial investment doesn't determine how long it actually takes to triple. The amount, if you're starting from $1 to get to $3, still takes you about 17 years. The same thing as if you were trying to go from $1 billion to $3 billion. Still takes you about 17 years regardless. Okay, so the entire idea here is that notice how easy it is to solve for t when we use the logarithmic form of compound interest, because now r and t are not exponents anymore. And it's equally as easy to solve for r, because if we were given the time instead of the interest rate, well, you would just be dividing by t on both sides instead of dividing by your interest rate on both sides. And that would just be it. Okay, so the takeaway here that I want you to really remember is if you're given a compound interest question, basically you just have to identify what it is you're solving for. If you're solving for the total amount, or if you're solving for the principal amount of continuous compound interest, you should use the exponential form, because once again, the exponential form allows you to solve for a or p fairly easily. If you are solving, however, for the rate or the time, then you should try to use the logarithmic form, because the rate and time are now linear, right? It's not part of an exponent. It's now linear. It's r to the first power and t to the first power. So it's substantially easier to solve for those. Okay. Okay, so that does it for chapter 4.2. There's nothing else to be discussed there, and now we're moving on to the last chapter that we're going to be discussing, logarithmic rules. Okay, so this is chapter 4.3 or section 4.3, whatever you want to call it, from the textbook if you're following along there. And again, what we are looking at today is logarithmic rules. So what we discussed earlier are 4 properties of logarithms. These are things that are universal for all logarithms. We also just looked at 4 properties of natural logs, but we saw that they were essentially equivalent, right? They translate back and forth. So what we need to do now is we need to discuss how to handle what happens when we add logarithms together, subtract them, or something else. Okay, so here are the 3 major rules. We have what is known as the product rule. So product rule. Okay, the product rule says if you have a logarithm with any base, I'm just going to call it a, and if you have 2 numbers or 2 values being multiplied inside of this logarithm, you can split it up into log, you keep the base the same, of your first value, plus log of, again, same base, of your second value. Okay, so another way to think about this is, okay, well, if I'm going in this direction, I'm splitting multiplication up into addition of 2 logarithms. But the main takeaway is if you have 2 logarithms being added together, as long as the bases match, you can condense it into one single logarithm and just multiply the 2 values together. You can multiply m and n together and just make it one log with the same base. So you can go in either direction here, and that'll help you either expand or condense your logarithm depending on what you're doing. Notice that if you're reading from left to right, you are expanding. You're taking one logarithm, turning it into 2. And if you're reading from right to left, well, then you are condensing, right? So expanding, condensing. Okay? So that is the product rule. And again, the product rule is really neat because it allows you to take 2 logarithms and turn it into 1, or 1 logarithm and turn it into 2. The hard part is just remembering what operations you're doing, right? Product rule, you think, oh yeah, you might be able to split this into 2 logs where they are being multiplied against each other. That's not the case. That would be very wrong. It's 2 logarithms separated by addition. Okay, if you want to have a little bit more background in this, you could always ask me privately. But the idea is that if you remember from one of our exponent rules, if we had x and x, right? If we have the same base and these were raised to, let's say, 3 and 2, what were you doing? You were keeping the base the same. So again, you're keeping the base the same. And what was happening to your exponents? Well, you were adding your exponents, right? Notice that the multiplication implied the addition of exponents. So this is x to the 5th. So if you're really seeing where this, logarithm rule comes from, it's being derived from the exponent rules. So now we have, if this is the product rule, intuitively you might think, okay, well, what's next? And what's coming next is the quotient rule. So quotient rule. And it's going to look pretty similar to what's going on in the product rule. You might actually be able to guess this one given the one above. So the quotient rule says if you have a logarithm with some base a, and you have 2 values being divided, you have a fraction going on inside of your logarithm, what you can do is you can split this up into 2 logarithms, once again, keeping the base the same, of your numerator minus logarithm, keep the base the same, of your denominator. Okay, so once again, notice you can read this in 2 directions, right? You can read this as reading from left to right. You are expanding. You are taking 1 logarithm and turning it into 2, or reading from right to left, the right-hand side to the left-hand side, you're taking 2 logarithms and you're turning it into 1. Okay, the hard part here, once again, is understanding that the division here implies subtraction here, or vice versa. Subtraction of two logarithms implies the division within one logarithm. And also, please don't get confused. I've had students in the past confuse the order of the values here, m and n. Your numerator is always going to be the first piece. Okay, your denominator of the fraction is always going to be the piece that's being subtracted. So this is, this is the actual subtraction here coming from your numerator, or I'm sorry, coming from your denominator. Geez, I really hope I didn't mess you guys up. One more time, I will say this. Your numerator is your first logarithm. Your denominator is your second logarithm. Okay, sorry about that. If I had an edit feature or a cut feature in YouTube, I would 100% do it, but I don't think it exists, so sorry. Okay, in any event, again, understanding you can condense or expand using your quotient rule, same as you can with your product rule. And last but not least, there's one more rule here that we have to understand, and this is known as the power rule of logarithms. So what is the power rule of logarithms? Well, the power rule says if you have some logarithm with some base of a, and it's on a value of m raised to an exponent, which I'm going to call r. This is the same thing as r coming out front as a coefficient, okay? So this is the same thing as r times the log base a of m, okay? So again, I was equating rules 1 and 2 to exponent rules. So again, rule 1 was if you have two bases being multiplied, what are you doing with your exponents? Well, you're adding them, right? So this implies, x and then your two exponents being added together. Your quotient rule, this is being derived from your exponent rule of if you have x over x, what you're doing, with your exponents. Well, this is the same thing as keeping your base the same, and then it's, one exponent minus the other. For the record, these are not zeros. These are just circling where your exponents would be. But the power rule is something entirely different. The power rule is not really coming from this. It's really hard to derive this just, without a proof. But the idea is just that as long as the piece here, your value, and your exponent attached to that value are inside the logarithm, you can take your exponent and move it out front, and that now becomes a coefficient, okay? So if we had, for example, log base 3 of x squared, this is the same thing as, again, understand the hidden implication here of the missing parentheses. The square is being directed to the x, right? This is going to be the same thing as 2 times log base 3 of x. These are equivalent statements, okay? And I want to really hammer this down, the placement of the exponent versus parentheses. If you had the same thing, log base 3 of x, but this time you had parentheses around the logarithm, and this is log base 3 of x, squared, this is not the same thing as log, 3x squared, which, again, means it's not the same thing as 2 log base 3 of x. You cannot go from here to here, okay? The reason is the square is being attached to the entire logarithm, whereas the square here is only being attached to the value inside of the logarithm. Two very different ideas. So please understand the difference between the two, because for this piece here underlined in red, you cannot use the power rule. It will not work out, okay? Okay, so with all of that being said, what I want to do is I want to practice, doing some expansions and doing some condensing. So let's do 1 or 2 together, and then I'll put you off to your next classwork assignment. So let's say we have the following. We have log base 2. So log base 2 of x squared times x minus 1 cubed, all being divided by 2x plus 1 to the 4th power. Okay, so there's a lot going on here. We have a lot of variables, we have a lot of exponents, and also what I really want you to understand is, again, understand the hidden implications. There is parentheses around, these pieces, right? This entire fraction is inside of this one logarithm. Okay, so with that being said, I want to try to expand this. So I will write expand. Okay, so I want to expand this, and to expand this, well, let's take it one piece at a time. I know I have multiplication going on up top, but before I handle that, let's handle the division, right? We have a fraction. The fraction is kind of the most obvious part of this entire piece. So I want to split the fraction up. Well, we have the rule, the quotient rule, which says if I have the logarithm and I have some piece over another piece, I can take it and expand it into two different logarithms where I have the log of the numerator minus the log of the denominator, right? So this is the same thing as log, we keep the base the same, it's still log base 2, of x squared times x minus 1 cubed, right? And that x minus 1 cubed, that's also very much still part of the log, but that cube is just being attached to the x minus 1. And the square is just being attached to the first x. Okay, so we have the first log, and now we subtract the second log, also base 2, of the following, 2x plus 1 to the fourth, right? So log base 2 of 2x plus 1 to the fourth. And again, understand this fourth, the exponent here, the 4, is being applied to the value inside the logarithm. It is not being applied to the entire logarithm. Two very different ideas here. As long as it's being applied to the piece that's inside the logarithm, then you're still in business for the power rule. Okay, so what I want to do is I still have multiplication going on, right? I have log base 2, I have this x squared times the x minus 1 to the third. So I want to split this multiplication up. So to split it up, well, this is log base 2 x squared, and now we're going to use the product rule. If we have two pieces being multiplied, it's log keeping the base the same of the first piece plus log keeping the base the same of the second piece. So I have log base 2 of x squared plus log base 2 of x minus 1 cubed. And we're still subtracting off that log, the log base 2 of 2x plus 1 to the fourth. Okay, we're almost done here. We know we're almost done because everything is split up now, right? We have no more multiplication going on. The only things that we have going on is we have exponents, right? So now what we're going to do is we're going to apply our power rule, which says, okay, well, as long as my power is being applied to the piece that's inside the logarithm, which it is for all three of these cases, we can take that exponent and move it out front, and that becomes our coefficient. So we're going to say, okay, well, this is equal to 2 times log of base 2 of x, right? The 2 moved out front, and now we just have x to the first power, right? So it's just 2 times log base 2 of x plus, okay, once again, we have this 3 here. We're going to move that out front. So now we have 3 log base 2 of x minus 1, and we're subtracting off minus, well, the 4 is also going to come out front, so 4 log base 2 log base 2 of 2x plus 1. And that's it. This is as expanded as you can make it. You cannot do anything else with this. So understand where we started, right? We started with one single logarithm, and we had multiplication and division going on, and this was kind of a mess, right? We had a bunch of x's, a bunch of exponents. How do you really handle this? The way that you handle this is you just try to break it down one piece at a time. Now, for the record, I went and I did the quotient rule first. So I did, log base 2 of, I split this up with the numerator, and I split it up, numerator minus the denominator, right? What you can also do, it's not incorrect to handle the numerator first and, handle it by using the product rule. If you do the product rule first, totally okay. It's just that, you just have to be careful of what you're doing, right? You have to also understand that you still have this division going on, and the division is still going to be applied to both of those pieces. Okay, so don't forget to take that 2x plus 1 to the fourth with you when you break it up the top, because if you lose it, then, well, you're going to have problems. Okay, So, but the entire idea for me, the easiest way that I find is just breaking the fraction up first. And once you've broken up the fraction, then you can handle the multiplication. And by handling the multiplication, we get 3 separate logarithms here. And when everything is said and done, we've gotten rid of the exponents and turned them into coefficients by using the power rule. So this is fully expanded. And you might be wondering, for the record, I'm just going to use the piece underlined here in green as an example. You might be saying to yourself, well, wait, isn't a power essentially just the same thing as multiplication? And to that, you are absolutely correct. So if we had log base 2 of x squared, this is really the same thing as log base 2 of x times x, right? But what is our product rule? Well, our product rule says if we have 2 pieces, we can split it up, right, and do the same thing. So we're going to do that. So this is really the same thing as log base 2 of x plus log base 2 of x. And you notice, oh, wait, I have the same piece here as I do here. So if I have 1 log base 2 of x plus another log 2 base of x, well, in reality, I have 2 of log 2 base of x. Okay? So all that's happening is the power rule allows you to simplify it without having to use the quotient, or I'm sorry, without having to use the product rule. The power rule is just a really useful tool to have under your belt. Okay, so you get the same result either way, the 2 log 2 of x. This is just, the longer way to go about it. But if you did have that question in your head, congrats to you, because, it is still important to understand what's really going on here. Okay, so that's how we work with expanding. Let's do some more expansion together. So occasionally you might be given, and I'm just going to start clearing this off now. Occasionally you might be given a scenario where they define for you the value of a certain logarithm. So what I mean by that is the following. Let's say given log base 5 of z is equal to 3, and log base 5 of y is equal to 2. And then I say evaluate the following. So evaluate log base 5 of y squared times z cubed. Okay, so the idea here is it's not asking you to find y or z. We don't care what y and z are, because we know that log base 5 on y gives you 2. And we know that log base 5 on z gives you 3. That's what we care about. So if we can split up this logarithm to be in terms of log base 5 of y and log base 5 of z, then we can just directly substitute in the 2 and the 3 if we can break up, the larger logarithm. So that's going to be our game plan here. We're going to be trying to break up this logarithm so that way we can do our substitutions and just plug in 2 and 3 and then get, an actual answer here. Okay, so let's try to break this piece up. We again have log base 5 of y squared times z cubed. Okay, the idea here is, again, we notice we have one piece times a second piece. So, and that's inside of a logarithm. So we know we can use the product rule. So the product rule says if we have 2 things being multiplied in one logarithm, we can split it into 2 logarithms separated by addition, and we keep the bases the same. So log base 5 of y squared plus log base 5 of z cubed. Okay, we're almost done, right? We have log base 5 of z and log base 5 of y, but over here we have log base 5 of y squared. Notice that that square is still being attached to your value, so you don't actually have y to the first power, you have y to the second power, right? So we're not done here. We can't, directly do our substitutions yet. This, once again, just last time I'm going to hammer this down, is very different than what I'm writing in red. It's very different than log base 5y quantity squared, right? The reason we know this is different is because now, if this were the case, we could directly substitute in the 2. But it's not the case, so, unfortunately, we can't do that. So we still aren't done. We have to simplify this down a little bit more. So simplifying this down a little bit more, well, that's really not that bad, right? We have y squared, and the square is being applied to the value inside the logarithm. So we know we can use our power rule and take that exponent and just bring it out front, right? So now we have 2 times log base 5 of y plus 3 times log base 5 of z. Again, did the same thing with the logarithm on the right. I brought that 3 out to the front because the power rule says we can do that, right? Our exponent can become our coefficient. And also vice versa. Your coefficient of a log can become your exponent. But in this case, that's not what we're trying to do. Okay, so now we have 2 times log base 5 of y and 3 times log base 5 of z. But notice that's exactly what we wanted, right? Log base 5 of y and also log base 5 of z. And we know what those are equal to. They're equal to 2 and 3 respectively. So we're just going to plug in, okay, well, this is the same thing as 2 times 2 plus 3 times 3. Okay, well, great. 2 times 2 is 4, plus 3 times 3 is 9, and that gives you 13. So when we've evaluated this, given the information that we were given, well, we're done. We got 13 as an answer. So all we did is, again, we broke up our larger logarithm to be in the fundamental components of the pieces that were given to us, right? The reason that we know that we wanted to get it into this form, is because we know what they are equal to. So that is our game plan. That was essentially the hint here. The hint is you're taking your larger logarithm and breaking it into those components so that way you can do your direct substitution for 2 and 3. And when you do that, we got 13 at the end. Okay, so with all that being said, I want you to do your second classwork assignment here. So your second classwork assignment is I want you to expand the following. So expand the logarithm of square root of 4xy over z. Okay, so try this out, try expanding it, see what you get when you handle this, and we'll talk about it in just a second. Okay, so let's tackle this together. First things first, before we even continue, what kind of logarithm is this? Well, this is a common log. You know this is a common log because this space down here where you would have a base is blank. And that's how you know that because it's a common log, well, it's indicative that your base is 10. Your base doesn't actually play a big part here. It actually doesn't play a part here at all, but it's just, refreshing your memory that this is in fact how a common log would look, okay? So how do we tackle this? How do we expand this? So we're starting with the log of this entire piece underneath of a square root, right? 4xy over z. And there's actually a couple different ways that you can go about this. I'm going to show the way that I normally go through it. However, again, keep in mind that there's a couple different ways that you can attack this, and there's no real correct way. I mean, there's a couple correct ways. There's definitely wrong ways, but there's no set correct way. So if you happen to get the same answer that I get, and you just did it in a slightly different order, that's totally okay. All right, so the first thing that I'm going to do here is again, I don't really want square roots, right? I don't want roots at all. The reason that I don't want roots is because logarithms are generally in terms of exponents, right? We think about logarithms similarly as we do exponents. So the first thing that I want to do is I want to convert my root to be an exponent. How do we do that? Well, again, remember, your index of a root is indicative of a denominator of a rational exponent, right? So, and everything else in here is to the first power. So we can say, okay, well, this is the same thing as log of 4xy over z, and this is all to the 1/2 power. Remember, they're all to the first power, so we know that our numerator of the exponent is 1, and the root is a square root, which tells us our denominator is 2, right? Okay, solid. Well, now what I'm going to do is I'm going to bring that I want to bring that exponent out, right? I'm going to use my power rule here. My power rule says, okay, if I have an exponent on the entire piece that's inside my logarithm, I can just bring it out front. So 1/2 times log of 4xy over z. So, okay, first step is done. We got rid of the square root. The square root was going to be annoying to deal with, right? So we got rid of it. Now what we can do is we can continue along and just split, do things by our, normal methods, right? So what we're going to do here is we're going to say, okay, well, we have, multiplication, we have division going on. So what I'm going to do is I'm going to handle the division first. So this is the same thing as 1/2 times log we keep the base the same. In this case, it's a common log, so we just don't write anything, of 4xy minus log of z, right? It's a logarithm of your numerator minus logarithm of your denominator. And the 1/2 is being attached to the entire thing, right? The 1/2 is being multiplied to the entire logarithm, so it only makes sense that 1/2 multiplies against every single piece inside. Okay, we continue along, we bring that 1/2 down. Now we see we have three things being multiplied here, right? We have 4 times x times y. So what I want to do is I'm just going to multiply, or I'm just going to use my product rule, I should say, and split all these up. So I now have log of 4 plus log of x plus log of y. And now we just bring down that minus log of z, and that's essentially it. We're basically done. The last thing that you can do if you really were determined to expand is you could apply the 1/2 to every single piece here. So this is the same thing as 1/2 log of 4 plus 1/2 log of x plus 1/2 log of y minus 1/2 log of z. And now this is fully expanded. Okay, so the idea here is we just took our we got rid of the radical, and we got rid of the radical just by using the definitions of roots, when in regards to rational exponents, right? We know that any root is the same thing as an exponent. We just needed to convert it to that form. Now that we had it as an exponent, we could bring it out front, and that's the same thing as pulling the 1/2 out to the coefficient. And the rest is just a matter of using the product rule and the quotient rule, right? So I did the quotient rule first just to get that minus z or minus log of z taken care of. And we use the product rule to split up everything else, right? So log of 4 plus log of x plus log of y. And then it's just a matter of clerical duty applying the 1/2 to every single piece. But now it's fully expanded. And I probably wouldn't take any points off if you left it here just because the last piece is kind of monotonous. Okay, so that's one way to handle it. I'm not going to go through the other ways. Again, if you got something effectively similar, that's totally great, and congrats to you, because again, there's a couple different ways that you can do it. You're essentially doing the same steps, just in different orders. So totally okay. All right. So good classwork assignment. Now, what we just talked about was a lot of expanding, right? So what I want to do now is I want to talk about condensing. So condensing is when we have a bunch of logarithms and we're trying to make it as few logarithms as possible, right? So let's say we have the following. We have, and I want to condense this. So let's say we have 1/2 times log of x plus 1 plus log of x minus 1. Again, I know I said this before. If you're not used to seeing brackets, you can just treat them like parentheses. We generally just use brackets to make things more readable. So instead of using a bunch of parentheses all in series, we kind of split it up with brackets to make it a little easier on the eyes. But in any event, they're effectively just parentheses. So what are we going to do here? Well, first, let's try to handle the logarithms. We see we have a coefficient out front, but trying to handle the coefficient while we still have 2 logarithms could get a little messy. It could get a little tricky. It's not impossible. It just gets a little bit annoying. So first, let's handle the inner piece. So I want to condense these 2 logs into 1 log. Now, the important thing here, and the thing that you should remember with expanding or condensing, is if you're expanding, when you take 1 logarithm and split it up into 2, you always have to keep the base the same. And when you're condensing, the first thing you have to check before you can condense is, are my bases the same? If the bases are different, you cannot condense. So we see here, oh yeah, we have a common log for the first one. We have a common log for the second one, which means they both have a base of 10. We're good to go. We can condense this. If they were different, you're stuck. That's it. You can't, with the tools that we have right now, you can't do anything more. It's as condensed as you can get. But as long as they have the same base, you're good to go. So, okay, let's try to condense this. We have 1 log plus another log. This is essentially the product rule, but going, in the reverse order. So we're going to be taking the addition of the two logs, making it one log, and we're going to be multiplying the values inside the logarithms together. So we're going to bring down this 1/2, and this is effectively one log now, where we keep the base the same. It's still base 10, so I'm omitting it. And now it's x plus 1 times x minus 1. Split up by addition. They have the same base. You can make them one log, same base, and just multiply the values together. Okay, so let's go ahead and actually do the multiplication. So doing the multiplication, we now have 1/2 times log of, well, this is just foiling, right? And even better, hopefully you guys recognize this, x plus 1 times x minus 1. Well, this is difference of squares, right? This is just difference of squares, but it's already factored. You're just going in the opposite order. So you should, I hope, know that you get x squared minus 1. And if you didn't see it immediately and you foiled it, totally fine as well. So, okay, log of x squared minus 1. And the last piece here is, notice we have this coefficient out front. We can now go ahead and remove these brackets. We don't need them anymore, right? So we have this coefficient of 1/2. So this is the same thing now as log of x squared minus 1 to the 1/2 power. And what we can now do, if we are really, want to convert this all the way, is the final form is log of the square root of x squared minus 1. Remember, 1/2 implies the root. The 2 tells you the index, so we know that it's a square root, and the 1 tells you the power of everything that's underneath the exponent. So this entire piece is to the first power, which means, it's just that entire piece. You can omit the first power thing. So again, just to quickly review what we did, if I wanted to condense, I'm taking two logarithms and smushing them into one logarithm, keeping the base the same. I then multiply them together because they were being added, right? If they were being divided, or I'm sorry, if they were being subtracted here, if this addition were instead a subtraction, then, well, your two pieces would be divided, right? Your first logarithm would be your numerator, your second would be your denominator, the values of them. Please do not make the mistake that I see quite often, and I'm sure as I say this, many of you are gearing up to make this mistake, and that's okay. I expect it, but don't make the mistake of thinking what this turns into. And I'm just gonna put this in red. This is not equal to log of x plus 1 times. Sorry, I put that parenthesis too early. Times log of x minus 1. Okay, these are not equivalent. The reason they're not equivalent is, notice you still have two logarithms. All you did is you directly changed the addition to be a multiplication, right? So this is now saying you have one logarithm multiplied against another logarithm, and that's not what the product rule is saying. The product rule is saying if you have two logarithms separated by addition, you can condense it to be one log where the values get multiplied. Okay, you're not multiplying two logs together, you're multiplying the values of those logs in one log. Okay, similarly, again, another very common thing that I see is if hypothetically this were a subtraction, so I'm just going to write a minus here, this is not equal to the log of x plus 1 over the log of x minus 1. Okay, these are not equivalent. The reason that they're not equivalent is, again, notice you haven't condensed anything. You still have two logarithms, right? You still have a log up top, a log on bottom. The quotient property of logarithms says when you're condensing, you are making it one logarithm, so one log, where the values of the two previous logs are getting divided. So where you would have x plus 1 over x minus 1. And of course, your base would be the same. Okay, so this right here, not correct. This here, 100% correct. If, this were a subtraction. Okay, I really just wanted to go through that because, again, I fully expect this error to be popping up, and this is one of the worst errors you can make for logarithms because, again, you have to realize what you're trying to do. Condensing means you're taking two things or more and putting them together, right? So you should expect, if you're starting with two logs and I say condense, you should expect that, oh yeah, I'm probably going to get less than two logarithms. So don't think you should get 1 and 2. You should think, oh yeah, I should get just 1. Okay. All right. So that is condensing, and that should just about do it for today. Let's see, how long have I been talking for? Yeah, about over an hour. That's good for today. So try your hand at the homework. We still have a decent amount of stuff left to cover, but we'll get to that in the next lecture that I post. Okay. So enjoy the rest of your day, guys, day, night, whenever you're watching this, and I will talk to you next time.